All right, welcome back. This is the lesson 4, product of water. We're just going to really go through the amphoteric nature of water and what that means for our solutions here. So water is amphoteric. It can react with either an acid or a base, and it can act as either an acid or a base. So here we have an acid, and the water here is acting as the base because it is accepting the hydrogen, right? The proton accepting. So at the same time, you could have a base, and the base could be accepting a proton from water and making water the acid. So here we have the accepting in the other direction. Or maybe let's call it donating in this case so that it makes it clear that it's an acid. Donating. All right, so with some very sensitive instruments, we've actually even found that pure water is just by itself, just water, nothing else, having two waters side by side will actually dissociate itself in this way, and it'll split some of the water molecules up into hydroniums and hydroxides. Of course, an equal amount of them, otherwise the solution would not be electrically neutral, which water is. But this is called self-ionization or auto-ionization, and this is a very interesting property of water. This indicates that there is an equilibrium, right? This is auto-ionization. It's something that's happening all the time, whether we want to or not, and it's between the hydronium and the hydroxide products. So if an equilibrium is established between hydronium ions and hydroxide ions and water molecules, then an equilibrium law could be written out. But of course, water is a pure liquid in this case, so we can't include a concentration. So we have to reduce this into a new equilibrium expression called Kw. This is the Kw expression. It's really important key expression to understanding acids and bases theory. So here's our Kw. At 25 degrees Celsius, this Kw, so this is our standard conditions, is 1 times 10 to the negative 7. So, the concentration of hydronium and hydroxide ions is 1 times 10 to the negative 7. Does that mean that there are a lot of hydroxides and hydroniums in pure water? Hopefully you said no, because this is 10 to the negative 7. Super, super tiny, right? It's less than a micromolar. Micro is 10 to the negative 6. So we have less than a micromole per liter of hydronium in there in pure water. So it's obviously not particularly acidic or basic. It's, well, of course it's neutral. And so this means that the value of Kw, if you were to complete this equation with this value I just gave you, 10 to the negative 7 molar, 1.0 times 10 to the negative 7 molar, then you would find that Kw is 1.0 times 10 to the negative 14. On the math side, we do see that there is a negative 7 and a negative 7, and under exponent law, we just add those together. So that's why it becomes negative 14. So if the ionization of water occurs by this equation, we can predict the effects of dissolving an acid or base on the hydronium and hydroxide ion concentration using Le Chaletier principle. So this equilibrium should shift to accommodate the extra hydroniums that are being created by the addition of an acid or a base. So when we add acid, the acid is producing a large amount of hydronium ions. That's the whole point. That's what we said. Even Arrhenius and Bronston-Lowry both told us this. And so the equilibrium will shift to the left. So it will shift to the left. So some of those hydroniums will be used up to make water and try to maintain the Kw. Since the equilibrium shifts left, the hydroxide ion concentration is reduced. Therefore, adding a strong acid to water increases the hydronium ions and reduces the hydroxide ion concentration. So with our little reaction, if we're adding a bunch of hydronium, then the reaction is going to try to shift this way by countering, by reducing both hydroxide and hydronium, but you just added a whole bunch. So now the balance will be that there are more hydroniums. Excuse me. Same difference if you added a whole bunch of base, then everything has to come back down so that you can increase your water. And that means that you're going to be left with more hydroxide than hydroniums. It'll be unequal amount now, and it'll be through this ratio, through the product constant. So here's an example. If we had 2.5 moles of hydrochloric acid, and I'm going to do the same hiding trick here. I'm going to do a little bit of hiding here. I'm going to hide. Maybe I'll do this, and then I'll hide the rest. Okay, so if 2.5 moles of hydrochloric acid is dissolved in 5 liters of water, so we have 5 liters of water, what is the concentration of the hydroxide ions? So they've given you 2.5 moles. How could you get 2.5 moles like that? Well, probably they mean that you could weigh out some sort of dried hydrochloric acid. In that way, it wouldn't affect the volume. It would only affect the amount of moles of hydrochloric acid. So here's our reaction. Hydrochloric acid, we need to remind ourselves exactly how many hydrogens or hydroniums we're going to get for every hydrochloric acid. Especially if it's reacting with water. And then we take the 2.5 moles and we divide that into the volume, and that will be our concentration of HCl. And that concentration of HCl, by the reaction we just wrote out, this HCl gives us 1 hydronium. This amount of HCl must be equal to the amount of hydronium or protons. So then I'm going to take my Kw. I'm going to put in this amount, this molarity here, into my hydrogen, and I'm going to use the Kw to figure out what is the hydroxide concentration through simple algebra here. So I replace the proton concentration with 0.5, my molarity, and then I adjust until I find that I get this value here. 2 times 10 to the negative 14. So this is interesting to think about, right? This means that if you add an acid, this is probably an important concept here. What am I doing? Okay, let's try deleting that there. Okay, so here's the important idea from this, right? That even after adding a strong acid to a solution, there is still a small amount of hydroxide left. So it doesn't absorb all of the hydroxide from that water because it's in equilibrium, because water is essentially acting as a very weak acid and base. It will always sort of accommodate a little tiny bit of hydronium here. So if you do the same thing, but you start with 0.4 grams of sodium hydroxide, and you dissolve that in water to make a solution with a volume of 1 liter, what is the hydronium ion concentration in the solution? So we divide out 0.4 grams of sodium hydroxide. This is the molar mass of NaOH. This gives us 0.01 moles. Take that divided by the liters. That gives you the new concentration of sodium hydroxide in solution. And then we take that sodium hydroxide, replace the OH value with 0.01 molar, and then recalculate to see what the value is. And the value we get is 1 times 10 to the negative 12 molar HCl. Or molar, no, not HCl, molar moles per liter of H plus. All right, and so we can try this for a couple more questions here. What is the hydroxide concentration if the solution with a hydronium concentration this is simply doing the Kw and the H plus rule times the hydroxide. All right, so these are very simple. These are, well, maybe not very simple, but they are simple extensions of our equilibrium law. There probably is a way we could apply an ice table here, but I think you're going to find that's not a lot of fun, because we would have to consider the initial starting concentrations, which would be 1 times 10 to the negative 7 for both of them. So it actually end up being quite complicated. In these cases, we're adding quite a bit of base, and so we can ignore the effects of the initial starting concentrations of hydroxide and hydronium. So this is technically an estimate. But it's good enough